Topic 4 of Unit 7 is called Simplifying Radicals. Well, if you're not even sure what a radical is, perhaps that's where we should start. So you'll, just looking down the page, you'll see a whole lot of square root symbols, right? Well, that square root symbol is actually called a radical symbol, okay? So when it says simplifying radicals, what we mean, in this case, is simplifying square roots. The radicand is the number, or numbers, underneath that square root symbol, or underneath the radical symbol. So radicand is the number or expression, because you can actually have a lot of stuff underneath there, or expression underneath the radical symbol. Okay, so we actually have some rules we have to follow when we're dealing with radicals, and that's where this lesson comes from. So for a radical expression to be in simplest form, the following must be true. A radicand, so the number underneath, can have no factors other than 1 that is a perfect square. And if you'll bear with me of just writing these down first, then I'll kind of go back through them and explain them in more detail. A radicand cannot be a fraction, and there can be no radicals in a denominator. Okay, you must rationalize the denominator, which we'll talk about later. So, if our goal is to simplify each of these problems, then that means we have to follow those 3 rules we just went over. So, number 1, we're just going to jump right in. It says simplify the square root of 75. It says a radicand can have no factors other than 1 that's a perfect square. So let's talk about 75, for example. Let's start listing some of the factors. Well, we've obviously got 1 times 75. It's not divisible by 2, but it is divisible by 3. 3 times 25. Not divisible by 4. It is divisible by 5. 5 times 15, I believe, yep. Not divisible by 6. Not divisible by 7, 8, 9, 10, 11, 12, 13, 14, 15. I think that's all of our factors, right? Now, as an aside, that process that we just went through of trying to figure out the factors, if that's something that you struggle with, just please keep in mind that you have a calculator available to you. And it helps to kind of make that list in the same way that I did, where you just start at 1 and start making your list, listing those pairs and how they produce a product of the number that you're working with, in this case 75, and reference that list. Don't try to do this part in your head. So, okay, so again, the rule said a radicand can have no factors other than 1 that's a perfect square. So looking at my list here, do we see any numbers that are perfect squares? Well, yes, obviously the 1, but the 25, right? 25 is a perfect square. Well, if I rewrite this problem, and instead of writing square root of 75, I write square root of 3 times 25, I have now created a product that can be simplified because this is a square root, okay? I'm going to kind of jump away for a second and come back to this problem, just to kind of pull from some of your knowledge that you've been using when you're simplifying exponential expressions. So just as a complete aside, just put a pause on that last problem. If I say, what is x squared, no. If I say, what is xy squared? Well, you've learned now that you can just distribute that square, right? So it'd be x squared, y squared. Well, in the same way, if I say, what is 2 times 5 squared? Well, this x and y is being multiplied as well, right? You just distribute the square. So it'd be 2 squared times 5 squared. Well, that's 4 times 25. So that's 100, right? You could also just kind of do it PEMDAS style. 2 times 5 is 10, and 10 squared is 100. So we know we did it right, okay? Point being, you took that exponent and distributed it to the 2 pieces in the parentheses. Well, let's apply that over here. A square root symbol, a radical symbol, is very similar to an exponent, and you'll learn soon that it actually kind of is an exponent. So if that's the case, then this square root symbol applies to both the 3 and to the 25. Well, if that's the case, can I take the square root of 3? Well, no, not have it create a whole number, right? But I can take the square root of 25. The square root of 25, I can pull out as just 5, right? And then I'm left with the square root of 3. This has now become our answer. 5 times, really this is being multiplied, the square root of 3. But we typically just don't write the times. A lot of people also read this as 5 root 3. You might hear someone say it like that. But we have now simplified this based off the fact that the radicand had a perfect square as one of its factors. Okay, we didn't have to worry about the other two rules. We didn't have any fractions or denominators to deal with. So let's just try that exact same process again. So 128, I want to look at the factors. Well, obviously 1 times 128. It's divisible by 2 because it's an even number. So 128 divided by 2, you can always type that into your calculator if you don't want to do that in your head. And you'd get 64. 3, well, the way you check to see if it's divisible by 3 is by adding these digits together. We get 11, so it's not divisible by 3. Is it divisible by 4? I'll look at the last two digits. It should be. So I'm going to type in my calculator, 128 divided by 4. So 4 times 32. Can't be divisible by 5. 6 maybe, nope, 7. You just want to try out a few to make sure that you've got all the perfect squares. It's not divisible by 7. I might type in 8. Ooh, 8 worked. 8 times 16. And so on and so forth, okay? So then I look to see, do I have a perfect square as one of those factors? And I do. Actually, I have 2. And because of that, that means that this is breaking one of the rules because we have perfect squares in our list of factors. So we need to break this apart into the square root of something times something, okay? So let's go with 2 times 64. I haven't changed the value of this expression because 2 times 64 is 128, but now I have made it to where I can pull out the square root of 64 and simplify this expression a little bit further. So square root of 64 is 8, and then I'm just left with the square root of 2. So 8 root 2 would be my answer there. Okay, I'm actually going to jump all the way across over here to number 4. Just kind of keep on trucking with these non-fraction problems. So number 4, square root of 27. Again, we need to list our factors. So 1 and 27. 2 is not going to work. 3 times 9. 4, 5, 6, so that's it, right? So I look to see, do I have a perfect square? I sure do, the 9. So I'm going to rewrite this as the square root of 3 times 9. And then I'm going to take out the square root of 9, which is just 3. So then I've got 3 times the square root of what's left over, which in there is a 3. Okay, we're going to move on to number 5. You'll notice that number 5 is a pretty large number, 1575. So when I go to start listing off my factors, I could be here a while, right? So it might be beneficial to start testing out some perfect squares rather than going number by number by number, okay? You can, so for example, you could look to see, okay, it's not divisible by 2 because it's not even. 3 times, well, I don't even know, so let's divide. 1575 divided by 3 gives us 525. I could continue this process, or I could think strategically. What are some perfect squares that I could try to divide this by, right? So 4, for example, would be a perfect square, but if that doesn't work, I notice that it's got 75 at the end, which makes me think that maybe 25 is divisible here. And it sure is. 25 times 63, okay? Well, I know that 25 is a perfect square right off the bat. So I'm just going to go ahead and go with that and not waste my time trying to find more factors. So I'm going to rewrite this, oops, try to keep my colors consistent, as the square root of 25 times 63. Okay, well, since I know that 25 is a perfect square, I'm going to go ahead and pull that out. So I've got 5 times the square root of 63. Now, I would box this in and say that we're done, except that we need to make sure that 63 is actually simplified all the way. When I look back at the problems I've already done, 3 is definitely its prime, so it's not going to have a perfect square as its factor. 2, we're good there. 3, we're good there. So this is the first time I've actually got kind of a big number in my radicand still, and I need to double check that that in and of itself doesn't have factors that are perfect squares. So I think, okay, 1 times 63. 2 doesn't work. 3 times 21. 4, 5, 6, 7 times 9. Oh, what do you know? 9 is a perfect square. So once again, I need to simplify this for a second time. So I'm going to rewrite this as 5 times the square root of 7 times 9. Well, when that's the case, I can again take out the square root of 9, which is 3, but I already have a number on the outside. Well, keep in mind that just like you've been dealing with your exponents, all of this is being multiplied. In between this 5 and the 63, that's a multiplication symbol that's hidden. Inside here is a multiplication symbol. So if this 5 is being multiplied, and I pull out a 3 to join it, I need to multiply those together. Really, I've got 3 times 5 times the square root of 7. So my final answer there would be 15 square root of 7. Okay? Now, to avoid this happening, you want to try to take out the largest perfect square you can find. And that's why it worked up here on these other problems. Like this number 2, we had the square root of 64 that we could have taken out, or the square root of 16. Because we took the bigger of the 2, it left the 2 on the inside that can't be broken down any further. Whereas over here, we took out 25. There was a bigger number, a bigger perfect square that we could have divided out, but we just didn't have it yet, and that's okay. You can do it in 2 steps. So look down at number 9. Number 9 already has a number on the outside of the radical symbol. That's okay. We're still going to look at the inside number, the radical, and focus on that to see if we can simplify it further. So my factors, 1 times 72, 2 times 36, and I'm going to stop right there because 36 is already a perfect square. Okay, so I'm going to rewrite this as 5 times the square root of 2 times 36. Now I know that I can take the square root of 36 out, which is 6, right? But if there's already a 5 there, I need to multiply those together. So 6 times 5 is 30 with the square root of 2 left over. Okay? Number 10, same thing. If you're feeling like you're getting this, you may want to try pausing the video and see if you can get it on your own without me walking you through it. And then just resume and see if you get the same thing. So I'm going to look for my factors here. What is that? 36. Using my calculator off screen. Yep, 36. And I'm going to just stop there because I've already hit a perfect square. So then I'm going to take that 36, go ahead and take the square root, which is 6. But I already have a 6 on the outside, so 6 times 6 is 36, root 3. So 11 and 12, same thing. Again, if you feel pretty confident, I would go ahead and just try to work these out without me. And then check back to see if you get them right. So really on this one, the biggest perfect square I can find is a 4. Usually they're bigger than that. Take it under 2, so I'd have 20 root 10. Okay. Now, all those problems we tackled with the same rule in mind, just the fact that the radicand cannot have factors other than 1 that are perfect squares. But we've left 4 problems here that all require us to use the second and third rule, where we know we cannot have a fraction and there can be no radicals in a denominator. So let's start with number 3. Number 3 says square root of, and then a fraction, 16/9, but it cannot have a fraction as the radicand. So the way we're going to deal with this is just by simply separating it. into the square root of 16 over the square root of 9. You are allowed to do that for the same reasons that we talked about, where we said if it's xy squared and you just distribute the square, it's the same thing. If you have x over y squared, you can just distribute the square. It's the same exact reasoning here. So we now, though, are dealing with another rule. It says there can be no radicals in a denominator. So now I have the square root of 9 in a denominator. Well, the good news here is that I don't really have to deal with the rule yet, because I can just simplify this based off my knowledge of square roots. What is the square root of 16? Well, 4. What is the square root of 9? 3. So my answer is simply 4/3. However, as you'll see in a little bit, you might come across problems where that's not the case. So let's look at number 6. Square root of 21 over the square root of 16. So it's already been separated for us, but we can't have this square root in the denominator. Well, lucky for us, square root of 16 is 4. Okay. However, square root of 21, we now need to deal with that and make sure that it can't be broken down further. So I'm just going to check my factors. 1 times 21, 2 doesn't work, but 3 times 7, that's it. Well, none of these are perfect squares, so we're actually good. This problem is already simplified as far as it will go. Number 7, can't have a square root in the denominator. So I'm going to leave that top one alone, but square root of 4 is 2. So I've taken care of that problem, but now I need to check the top. So 1 times 32, 2 times 16, 4 times 8, etc., etc. I'm going to go ahead and go with the 16 here. Even though the 4 is also a perfect square, I'm going to focus on the 16 because it's larger. So now I'm going to break this down into the square root of 16 times 2. All over 2. Now I need to pull out that 16 from underneath my radical symbol, which becomes a 4. So I've got 4 root 2 over 2. Now you'd think we'd be done because the 2 obviously cannot be simplified anymore on the inside. We don't have a radical on a denominator. However, we have a fraction here that can be simplified, just a plain old fraction. What's hard to tell is that 4 and 2 here can actually be simplified. Remember the 4 root 2, this piece right here, that is all one thing. It's being multiplied together. However, that doesn't mean that we can't still divide it out when considering the denominator. So 4 divided by 2, or just even picture dividing both the top and bottom by 2. That's going to give you 2 root 2 over 1, or you can just leave that part off. So you've got 2 root 2. Okay. Last one on the top section. Again, I'm going to rewrite this as square root of 18 over square root of 64. That gives us 8 on the bottom, square root of 18 on the top. So again, the fractions actually weren't an issue here. You'll learn on our next lesson, topic 5, how to rationalize a denominator. So like if this denominator had said square root of 18 over square root of 7, you can't actually just take the square root. So you'll learn in the next lesson how to deal with that. But for now, let's just keep on going with what we're doing. So square root of 18, I need to make sure that there aren't any factors that are perfect squares. And there are, because 9 is a perfect square. So I'm going to rewrite this as a square root of 2 times 9 over 8. I'm going to take out that square root of 9, which is a 3. So I've got 3 root 2 all over 8. The 3 and the 8 cannot be simplified further. So I am done. Okay, almost there. This is a short notes page. The final thing is just kind of considering the operations that you might do with radical expressions. And we're only going to just dabble in this a little bit to help you further extend your understanding of how radicals work, but you'll explore this even more so when you get to geometry and algebra 2. So when you're multiplying radicals, you are simply going to multiply the coefficients in front of the radical symbol and the radicands. Kind of going to play the matching game there. And then you simplify if needed. So looking at number 13, we've got 3 square root of 7 times 11 square root of 3. You could rewrite this because, remember, these are being multiplied. You've technically got 4 things that are being multiplied together. And we know that we can rearrange these and have the same product. So I could put the 3 and the 11 next to each other, the 3 and the 7 next to each other. Then I can multiply these, which is 33, and multiply these, which is 21, which would have been the same as if I had just looked at it from the start and said, okay, what is 3 times 11? And I get the 33. And what is 7 times 3? And I get the 21. Now, before I call this problem done, though, I need to first check to make sure that that 21 is simplified as far as it can. So I'm going to check my factors. 1 and 21, 3 and 7, and that's it. So this problem is complete. So then looking at number 14, again, same thing. You're going to multiply coefficient with coefficient and radicand with radicand. Just so happens this one doesn't have a second coefficient, so we're going to do 2 times the square root of 96. But now I need to check that 96. So 1 times 96, 2 times 48, 3 times something, 32. Yep. 4 times something, using my calculator, 24. 5 should be divisible by 6 because it's divisible by 2 and 3. 96 divided by 6 is 16. There's a perfect square that I can do something with. So I'm going to focus on that 16, break apart my radicand here to be 2 times the square root of 6 times 16. Take that 16 out, which is an 8. I mean, a 4, because you're taking the square root. But then 4 times 2, that's where the 8 comes in. And then you're left with square root of 6. And there's your final answer. So 15, again, you can just multiply radicand times radicand, and you get square root of 100. Well, what is the square root of 100? It's just 10. Okay? Which, just kind of glance at that for a second again. If you're going to multiply the square root of 10 times the square root of 10, your answer's 10. Just keep that in mind. Okay, number 16, again, we're just going to multiply the inside times the inside. We get square root of 15 times 6, which is 90. Then we need to break that down. I can tell right off the bat 9 times 10 would work, right? If I break this into 9 times 10, take out that square root of 9, I've got 3 root 10, and I'm pretty confident that 10 cannot be broken down any further. 1 times 10, 2 times 5, that's about it. Number 17, okay, here's where we have to apply our exponent knowledge. We can distribute that square to the different pieces, the different factors within that expression. So just like if this had said xy squared, we distribute the 2 to each piece there, we're going to do the same thing. We're going to distribute the square to the 3 and distribute the square to the square root of 5. Okay? Now, you could see it that way, or you could see it the long way, just like we taught you with exponents. You could see this as 3 square root of 5 times 3 square root of 5. Okay, and then you're just doing, again, radicand times radicand and coefficient times coefficient. Well, if that's what we do, then we're going to get 9 times the square root of 25. Well, what is the square root of 25? Square root of 25 is just 5. 9 times 5, then, is 45 for our final answer. Now, looking back up at that problem, again, how I showed you over here, the square root of 10 times the square root of 10 gave us 10. Well, same thing down here. Square root of 5 times square root of 5 ultimately gave us 5. Okay, we just happen to have the 3's as well. So on number 18, let's think about it that way. If I've got 5 root 3 times 5 root 3, well, 5 times 5 is going to give me 25. But square root of 3 times square root of 3 is just going to give me 3. You could see it the long way, as square root of 3 times square root of 3 is going to give you square root of 9. But the square root of 9 is just 3. My final answer on this one would be 75. Okay, so that is just a very quick exposure to simplifying radicals. Hopefully, if you understood just the general practice, kind of like what we did here on number 10, where you're pulling out the perfect square and its square root, then you should be pretty good to move forward with this class. Some of these problems were a little bit unique, especially at the end. But if you understand the general gist of looking at the factors of the radicand and pulling out any perfect squares, then I would consider today a success. Make sure you talk to your teacher if you have any questions. They'd be happy to help you.